Hi guys, and welcome to our last topic for Unit 7, and that is topic 7.6. We're going to look at polarity, and we're going to look at that through two different lenses, and that's why I had you guys work through that article, understanding the polar bears and the penguins and how they were trying to mimic electronegativity and ultimately electron sharing within a bond and within a molecule. And so if we go back, this is kind of tying a big ribbon on the topic that we've started with chemical bonding. And so the idea is we have a couple of things to review. We talked about the periodic table and some different trends. And one of the trends that we discussed was what's called electronegativity. And again, on that comic that you read, it had the polar bears and penguins. And the idea is that you saw that elements became more electronegative as you moved to the right and up. It left out the noble gases. And the whole idea with electronegativity is going back to this idea that you want to attract electrons. And so when we look at the periodic table, fluorine is only one spot away from having its octet complete, and it has a very small atom. So fluorine is desperately trying to get that one electron to fill that octet. And then that starts to explain the reactivity and the nature of fluorine. And that's the idea, to get that bond in order to, again, make that octet complete. And so, like we just mentioned here, is that it increases across a period and down a group. And it's been a while since we've decreases down the group. And the idea is, if you remember, periods are your horizontal rows, groups are your vertical columns. So the trend for electronegativity is that as you move up a family and to the right, that's the trend for how electronegativity increases. Again, noble gases are not included in that because noble gases have a complete octet, and they are not looking to gain or lose electrons because they have that S and P configuration filled. And so because we have electronegativity differences that desire to attract electrons, we get what's called polarity in a molecule. And basically what that looks at is how are those electrons shared? And they might be shared more evenly or less evenly depending on that difference. And so from the difference in their electronegativity, this goes back to what we started this whole unit with topic 7.1, just looking at the generic properties of a chemical bond. And so where these types of bonds come from and properties of them is from their electronegativity to get to their octet. So we have three types of bonds, and we talked about there's three types with ionic, covalent, and metallic. We're kind of leaving metallic bonds out. Yes, they're important. We just don't really emphasize them at this point. So what we really say is that we have three types, and that covalent has two different kinds. There is a nonpolar and polar covalent bond, and then we have ionic. And ionic is essentially a very extreme polar. And so there's distinct differences on what's taking place here. In a nonpolar bond, that's when we have electrons being equally shared. And so it's kind of like a game of tug of war between the atoms and how well do they share the electrons between each other. And so this is when basically the electronegativity difference is very small, that they're very close to each other in terms of strength, and that if you think about playing a game of tug of war with yourself, it would come to a draw because, again, if you're playing against yourself, one side wouldn't be able to win over the other. So the type of elements that you see typically in things that are nonpolar are basically things bonded to itself. So we're going to get into this more, but there are 7 diatomics, and we've drawn some of them already. And so I have another acronym to help remember this. So the diatomics I remember by the silly phrase of Hoffen-Kleiber. And Hoffen-Kleiber is like, we've drawn H2, we've drawn Br2, I believe we've drawn N2. So there's these 7 elements that exist this way. So again, it's like it's in a game of tug of war with itself. And so we're going to talk about this electronegativity difference here in a moment. But if the difference is less than or equal to 0.4, then it would be considered a nonpolar bond. So polar is sharing of electrons. That's the one key thing that these share in common in covalent, is that they're sharing electrons. However, sometimes they're like toddlers and they don't necessarily want to share all that fairly. And so when we are describing polar bonds, we are looking at an unequal sharing of the electrons. And that's when we get a stronger difference in electronegativity. So one element is winning the game of tug of war, or seems to have a little bit of a head start on those other elements. And so the atom with more electronegativity takes the electrons closer. And so this starts to lead into another topic that we're not going to get into, which is intermolecular forces, or IMFs. And so we get into these things called dipoles. And we just unfortunately don't have time to really discuss them. And so if you go on to AP Chemistry or C Chemistry later in your future, you'll definitely get more of a taste of those. And so these are same thing, that they occur between two nonmetals or metalloids, but we have a difference, or a greater difference in their electronegativity. So ionic bonds, like I mentioned already, they're basically an extreme polar bond where the electronegativity is so great that the electron is lost by the metal, given to the nonmetal. So that nonmetal has so much of a greater electronegativity, such a higher attraction for electrons, that again, the metal just kind of gives up and gives the electron away without much of a fight. And so you have an electronegativity that's greater than 1.7, and typically, again, it's a metal and nonmetal. And again, that all ties back to electronegativity and what's the difference. So if you were to look at the type of bond that would form between two specific elements, what you see here is we have Cl and Mg. And so we'll say that we have Cl here and Mg. What we need to know about each of them is their electronegativity. And so I have a periodic table for you that has just their electronegativity values on it. That's all we're going to use this for. And so if you take a look, chlorine has a value of 3.0 and magnesium is 1.2. So you're going to find the absolute value of the difference. That little triangle is delta. That means difference in our electronegativity, and the bars meaning absolute value. So just don't have a negative. Typically, I just always take the largest minus the smallest. So what you're going to do is take 3.0 minus 1.2. And when you do that, you get a difference of, let's see, looks like 1.8. So because we have a difference here that's greater than 1.7, this means it's an ionic bond, specifically between these two elements because of the difference in electronegativity. So magnesium is just going to give up its electrons altogether. So in the next example, we have hydrogen and oxygen. Go to our table here. Hydrogen's 2.1, oxygen is 3.5. And I already had a goldfish moment, 2.1. There we go. 3.5. It doesn't matter what order, again, you subtract here. I just like to put my larger electronegativity from my lower. Does not matter. The big thing is take the absolute value or don't have a negative sign. So if we go ahead and subtract those, we get an answer of, it looks like 1.4. Okay, so again, you follow with where it falls within these ranges. It's definitely in between that 0.4 to 1.7 range. So this means it's a polar covalent. So what's taking place here is they are sharing electrons. However, oxygen is much greedier than hydrogen, so there's an unequal distribution taking place here. So the last one, carbon to sulfur. We have carbon with an electronegativity of 2.5, and we have sulfur with 2.5 as well. If you go to Google, for example, and look up different electronegativity values, they sometimes vary depending on the publisher. So just try to stick with the one that I provided. And when we find our difference here, there is no difference. And so that means that they are basically in a tie with one another. And so that this is going to be a nonpolar covalent. And those electrons are going to be shared. And they're getting along at this point. And they're going to share those electrons equally in the bond. So this is looking at within an actual bond. the last thing we have to do on this unit is looking at within the whole molecule. So, for example, what we just did is we were looking at the bond, say, between H and O. So just real quick on the side, if we drew the Lewis structure for water, what we just did is we looked up the electronegativity of hydrogen and oxygen. And so what we were determining is this very specific bond, what does that mean in terms of how is it sharing its electron? The backside here is looking at the polarity of the whole entire molecule. So overall, at a larger perspective, what's taking place here. So there are 3 rules to follow. You can tell a molecule is going to be polar or nonpolar based on these 3 things. A molecule will always be polar if it has any lone pair of electrons on it. For example, if we look at the Lewis structure of ammonia, we have 8 electrons. Nitrogen's your central atom, surrounded by 3 hydrogens, and a lone pair on the central atom. As soon as I see that lone pair here, that is how I know that it's polar. Does not matter how many lone pairs you have on that central atom, it's going to have the electrons gravitating towards the nitrogen. So nitrogen's going to hog the electrons. Hydrogen's unfortunately not going to get a fair share of the electron pool. We have another way that a molecule results in being polar, and that's if it's surrounded by more than one type of atom. And that gets into that, in this case, we have fluorine and chlorine, that we have different electronegativities pulling on that carbon. So when you get your total for electrons here, you'll discover you have 32 electrons to spend. And so the Lewis structure has carbon in the center, 4 surrounding atoms, 2 of which are fluorine, 2 of which are chlorine. You have enough to complete the octets on your outside atoms. And so the idea is, if you think about it, carbon is stuck in kind of an odd tug of war. You have chlorine pulling from both sides and fluorine pulling from both sides with different resulting electronegativities. And so because of that, each of these individual bonds then take on a different role of being ionic, polar, or nonpolar, depending on the situation. This is going to be a polar molecule. So we have chlorine is one type that it's surrounded by, and we have fluorine surrounding it from another side. That's where we get the idea that this is a polar molecule. So the only way that a molecule is nonpolar is that it cannot have lone pairs. So the first thing is no lone pairs. And then the second rule is it has to be surrounded, and it should say is not surrounded. So your notes will be fixed by the time I post them. So they are not surrounded by more than one type. So when we go to draw this Lewis structure, we have carbon in the center, 8 electrons. And so this is a very fair distribution. So electrons, there's no extra electrons on carbon. So what this tells us is because it's in essentially a draw between these 4 hydrogens, all the electrons are being shared or pulled upon by the carbon equally and the hydrogen from all 4 sides. Therefore, because they are being shared equally, this is a nonpolar. So the last thing is just 3 more practice problems doing what we just did. Looking at the Lewis structures for water, and I kind of gave it away here. Water is HOH. Like Vesper, again, we're looking at the central atom. So the first thing is, do I have lone pairs? And I can see right away that yes, in fact, I have lone pairs on each of these. So again, as soon as you see lone pairs, that's rule A. This is a polar molecule. Oxygen does not play nice, and it's not going to share. So the next one, we have silicon tetrabromide. Silicon's the center, surrounded by 4 bromines, each of which have enough electrons to complete the octet with a grand total of 32. So when we look at the structure, the first thing I look for is, does my central atom have lone pairs? No. So the next thing I have to look at, is it surrounded by one type of atom or multiples? It's surrounded by all of the same variety, all bromine, with all the same electronegativity difference on each of these individual bonds. Therefore, this is going to be a nonpolar molecule, and therefore it will share electrons equally. So the last one is CO2. CO2 has a couple of options for the Lewis structure. The one that gets drawn most frequently involves a double bond on each side. Just so you know, there is a resonance structure. The other way you can draw this involves one of the oxygens being triple bonded, one of them having a single bond. Both are correct. Both get you the same answer. You look at your central atom. Are there lone pairs on the central atom? And in both scenarios, the answer is no. The next thing you have to look at is it surrounded by more than one type of atom? Again, it's surrounded by oxygen on both cases, so this is also going to be a non-polar molecule. So this was just a brief introduction to polarity in terms of electrons don't have to be shared equally in a covalent bond. Again, if you take chemistry and see it in the future, there's definitely a lot more that develops from this concept. So this is the end of Unit 7.